Hello everyone, this is Yashwant Jersam. Today I'm here to give a presentation on text classification, its techniques, frameworks, and real world applications, along with my teammates Harshita Jangama and Abhinav Alladi. Moving forward, these are the following contents which we are going to look in this presentation. In this slide, we are going to begin by discussing text classification. It's a crucial technique within the field of information retrieval. It is an automated process of assigning predefined categories or labels to text documents. In simple terms, we can say it's about teaching computers to sort and organize text. This is a very crucial component in many information retrieval systems. Think about how search engine works. They kind of use text classification to categorize web pages, allowing them to provide more relevant results or queries, or consider spam filters which classify our emails as inbox or spam. It enables us to structure and make sense of huge amounts of textual data, which is essential for effective information retrieval. In the following sections, we'll explore various methods and applications of text classification, and we exactly get to know how fundamental it is to retrieve the information we need. Text classification pipeline. These slides will outline the standard workflow for the building a text classification system from data preparation to the deployment. First one, data collection and preparation. Moving on to corpus assembly, gathering relevant text documents from variety of sources that help model learn various things and train on the data. Data cleaning. This is a crucial step where irrelevant data is removed, errors are corrected, and the text is normalized to ensure the consistency of the raw data. Data splitting. The dataset is divided into training, validation, and test sets. The training set is used to train the model, and the validation set to tune hyperparameters, and the test is to evaluate the model final performance. Data augmentation. To improve the model's robustness and generalization, additional training examples can be generated using techniques like synonym replacement, back translation, and paraphrasing. Step 2 of workflow, which is pre-processing. Tokenization. The text is basically divided into smaller units, such as words, subwords, or characters, in which we call them as tokens. Normalization. Text is transformed to a standard format by lowercasing, removing accents, and normalizing the spellings. Noise removal. Unwanted elements like special characters, HTML tags, and extraneous symbols are completely eliminated in this step. Stop word removal. Common words that don't contribute much meaning of the text. For example, the, is, and words like these are removed. Stemming or lemmatization. Words are reduced to their root form to handle morphological variations. Moving to the next step of workflow, feature extraction and selection. Here we have vectorization, where the text is converted into numerical vectors that machine learning models can process. Common methods include like bag of words, word embeddings, dimensionality reduction. Techniques are used to reduce the number of features, which can improve efficiency and prevent overfitting. Feature weighting. Different weights are assigned to different textual features to reflect their importance. N-gram extraction. Sequence of words are extracted to capture some textual information. In this slide, we have two steps of workflow. We'll start discussing the model selection and training first. Here we have algorithm selection. An appropriate classification algorithm is choose based on the characteristics of the data and classification task. Hyperparameter tuning. The model's hyperparameters are basically optimized techniques like grid search, Bayesian optimization, training regimen. Parameters such as batch size, learning rate, epochs, and the optimization algorithms are configured here. Regularization. Techniques like L1, L2 regularization, dropout, and early stopping are applied to overfitting the data. Moving on to the next step, evaluation and iteration. Performance assessment. The model's performance is measured using appropriate evaluation metrics to prevent errors. Error analysis. Patterns in misclassified instances are identified to understand the model weakness. And model refinement. The model is adjusted based on the evaluation results, which may involve changing parameters, features, or pre-processing steps. And the next one, ensemble methods. Multiple methods are combined to improve the performance and robustness. Last but not the least, deployment and monitoring. Model serialization. The trained model is saved in a deployable format. Inference optimization. Techniques like pruning, quantization, or distillation are used to improve the prediction speed. Performance monitoring. The model's performance is tracked in the production environment. Feedback loop. New data and user feedback are incorporated to continuously improve the model performance. These slides describes various techniques for extracting and engineering features from text data, which are crucial for the performance of text classification models. The first technique is lexical features, bag of words. This method represents documents such as counts of individual words, disregarding grammar and word order. Term frequency. It measures how often a term appears in a document. Term frequency inverse document frequency. This technique weighs terms by their frequency in a document and their rarity across the entire corpus. Second technique, syntactic features. Here we have part of speech, grammatical categories of words that can indicate document style or topic, dependency relations, grammatical relations between words in a sentence, parse tree features, information extracted from the syntactic parse tree of a sentence, semantic features. Here we have named entities, identification of entities such as individuals, organizations, locations, and dates. Topic models, techniques like latent digital location are used to extract topics from the documents. These slides cover traditional machine learning algorithms commonly used for text classification. Now we'll look at probabilistic classifiers. Here we have naive apply naive theorem with strong independence assumptions between features. And we also have three types of naive. They are multinomial suitable for discrete features, Bernoulli naive suitable for binary features, Gaussian naive suitable for continuous features. Moving on to linear models, we have logistic regression, models the probability of class membership using the logistic function. Also support vector systems, find the optimal hyperplane that maximizes the margin between classes. And we also have two types, they are linear SVM and kernel SVM. Passing to decision tree methods. We have decision trees, hierarchical structures that split data based on feature values from forests. Ensembles of decision trees trained on random subsets of data and features. Next, instant-based methods. We have k-nearest neighbor. It's one of the biggest example that is used in industries that classifies instances based on majority class of the k-nearest neighbors in the training data.
Hello, Professor. I'm Harshita Janagama. Moving beyond the traditional methods of the deep learning, now we'll see the text classification with deep learning, which is neural network fundamentals and feed-forward neural networks. In the neural network fundamentals, we have neurons and the activation functions that performs the basic computations, and activation functions like sigmoid and tanh are used to introduce non-linearity. And backpropagation, that is the main algorithm for training neural networks. and is used to calculate the error for the neural networks. And algorithms like stochastic gradient, RMS prompt are used to minimize the loss function. And the batch normalization weight decays are included in the regularization methods, which are employed to prevent overfitting. Feed-forward neural network. In this, the layers of interconnected neurons, which the information flows in only one direction and is used for text classification when the text is converted into fixed length vectors. And the limitations would be it doesn't handle sequential data well. And we have more methods of it like CNN, iconic architecture, RNNs, and we'll see the variations of it. So CNNs use convolutional layers to detect the local patterns, and the pooling layers will reduce the dimensionality of the data. And in text classification, 1D convolution can identify like single gram patterns, n-gram patterns, would say. And if you count on the benefits, CNNs offer positional invariance, detecting the patterns regardless of their positions, hierarchical pattern detection, and parameter sharing. And coming to the iconic architectures, text CNN uses multiple filter sizes to capture the different n-gram lengths. Like VD-CNN is a very deep CNN for text, and character level CNNs which process text at a character level. And RNNs are designed to process sequential data. They have loops that allow information to persist and is also suitable for modeling sequential relationships in data. And the challenges would be that would suffer from vanishing or exploding gradients, and variations would calculate as a long short-term memory, and gated recurrent networks, which are improved versions of the RNNs, which addresses the vanishing gradient problem here. RNN structure is like trees, and the text applications are they can capture hierarchical structures in language, such as the causality and semantic roles. Limitations of it are it requires more parse trees, which are computationally intensive. And the hybrid architectures, these combine different neural network architecture to strength. For example, CNN LSTM, which extracts the local patterns, and LSTMs model sequential dependencies. And the attention-based RNNs, attention mechanism are added to RNNs to focus on the relevant input paths. Hierarchical networks model text at different levels, like word, sentence, and document. Multi-channel architectures that uses parallel networks to process input in different ways. And now this will focus on the transformer. That's a powerful architecture that has revolutionized text classification and NLP. First, attention mechanism basics, self-attention, which is the model to weigh the importance of different words in a sentence relative to each other. Multi-head attention that performs attention multiple times in parallel, capturing different relationships between words. Scale dot product attention that is a specific way for calculating attention weights using the dot product. Position-wise feed-forward networks process the representation at each position in each sequence. Transformer architecture. In this first one would be encoder-decoder framework. The framework is in original form has an encoder to process the input and a decoder to generate the output. Layer normalization, it normalizes the activations within the layer to stabilize training. Residual connections adds the input to the output of sublayers to help with the gradient flow. Positional encoding. Since the transformer will not use RNNs, positional encoding is used to give the model information about the order of the words there. After seeing all the transform-based models, now we'll see how at the output the text classification is evaluated. in between the like four fundamentals: one, accuracy, precision, F1 score, and recall. Accuracy, that is the proportion of the correctly classified instances, and the limitations would be imbalanced data sets. And for the precision, that is calculated as true positives among the positive predictions, and which measures exactness. And the recall value, that is proportion of the true positives retrieved, and interpretation of the recall value, it also measures the completeness, and like also called as quantity of retrieval. F1 score, which is the harmonic mean of the precision and recall. Uh, Applications when balancing between the precision and recall, F1 score is required. Looking into the more evaluation metrics, one is multi-class evaluation and the multi-label evaluation. In the multi-class evaluation, we have macro averaging and the micro averaging. Macro averaging is one side which calculates the metrics for each class individually, whereas the micro averaging, it adds up all the class contribution and then calculates the metrics. And in macro averaging, that gives equal treatment for all the classes regardless of their size. But whereas in the micro averaging, that gives more weight to the larger classes. And coming to multi-label evaluation, we have four features here: Hamming loss, subset accuracy, and a label-based F1. Hamming loss is a fraction of mispredicted labels that calculates the mispredicted labels, and the fraction of instances for which all labels are correctly predicted, that is subset accuracy. For example, example-based F1, F1 per instance, and then it is averaged. Label-based F1 is F1 per label and then averaged.
Hello everyone, this is Abhinav Alladi. I'm going to present the further slides from here on. Cross-domain text classification. In real-world scenarios, label data is often scarce in the target domain, while the transferring knowledge from a source domain can be very beneficial. However, differences in feature distributions are also known as domain shift, and it poses certain challenges. We discuss methods such as domain divergence measures, transfer learning bounds, and domain invariant representations, which help bridge this gap. Additionally, we explore certain instance-based adaptation techniques, which includes instance weighting, importance sampling, selective sample transfer, and multi-source weighting to refine the adaptation process. Multilingual text classification includes representation models and language-specific adaptation. Challenges in multilingual text classification discusses difficulties such as different scripts, grammar structures, data scarcity, and computational requirements. There are certain approaches to multilingual text classification where different methods are explained, including separate monolingual models, translational based approaches, and multilingual models. The real world applications of text classification. Here are some of the applications which are not sentimental. For example, news categorization, email filtering, document management systems, social media content moderation, product categorization in e-commerce, academic paper classification, legal document analysis. In the further slides, we will study about the sentimental real-world applications. Despite progress, challenges persist. Here we can see certain challenges which includes class imbalance, linguistic nuisance, computational costs, interpretability. in class imbalance. For example, hate speech is often misclassified. When we speak about linguistic nuances, the idioms like break a leg confuse models. When computational costs are considered, training BERT requires GPUs and days of compute time. In the similar way, interpretability has deep learning models which are black boxes, meaning hard to debug or explain. Future trends. Looking ahead, self-supervised learning, few-shot learning, and domain generalization are key research areas. Here, the models that can learn from a limited labeled data and generalize across domains efficiently will define the success of the future of cross-domain classification. To conclude this presentation, to summarize, the text classification evolved from rule-based systems to transformers. It's really very ubiquitous from spam filters to healthcare. The challenges like bias and scalability remain open problems. The future is so hybrid, which involves combining neural networks with symbolic logic for robust, interpretable AI. As you can see, the data grows, so will the impact of this technology. Here are some of the references which were very helpful in making this presentation. The references continue in this slide, and that's a wrap. Thank you so much, everyone, for giving this wonderful opportunity.